so questions on electromagnetic induction. So remember, this is our key formula. E is minus n, change in flux over change in time. Remember, it's not exactly like that in your tables, okay? Remember, flux, if we don't have that, B by A in the table, it's the definition of magnetic flux. The time, our favourite formula, velocity is distance over time if we're in trouble on time, and very occasionally we can use Ohm's law. So EMF being voltage equals IR. So we have our core formula and we have our three formula that go around it. Okay, so that's the toolbox, that's what we're using. So let's start here. So to calculate the magnetic flux, we're making our list, passing through an area of 3 square meters, so that's fine. Magnetic flux density 40 millitesla, so be careful with the milli, 10 to the minus 3. We're looking for flux, so this is just the definition of flux, B by A. So it's 3 times 40 by 10 to the minus 3. That's 120 by 10 to the minus 3, 12 by 10 to the minus 2, 1.2 by 10, so it's 0.12 of a Weber, isn't it? So check that. 3 multiplied by 40 exponential minus 3. Yeah, okay, so 0.12 Weber. Second one, okay, calculate the EMF induced. So we're making our list again. EMF induced when the magnetic flux cutting a coil of 150 turns, so N is 150, reduces by 5 Weber. So Weber is the unit for flux. Okay, so that's flux is 5 and T is 2. So this is Faraday's law, so the core formula. But in this case we have everything. So this is just the introduction to it. So we have 150, the change in flux, it decreased by 5, so that's by 5, and it took a time of 2 seconds. So it's 2.5 times 150, so that's 375 volts. Remember, the minus is there, you can leave it there, it's to do with Lenz's law. We're not concerned about it, you won't be penalized if you don't have it. Question 3. Okay, so this time a circular coil of 200 turns. So okay, circular, you're interested in that. N is 200. The radius of the coil is 6 centimeters, so 0.06. Perpendicular magnetic field of flux density 3 millitesla. So this time it's the flux density you've been given, 3 by 10 to the minus 3. You're asked for the EMF induced when it rotates through 90 degrees in 1/5 of a second. So the time is 0.2. Now, remember, if it rotates through 90, if it's perpendicular to the field, so the field is going from left to right, so this is perpendicular to the field. If I rotate it through 90, it's now parallel to the field, and the flux will be 0. So the flux it was at the beginning is the change in flux, because at the end it's 0. So it's the flux at the beginning minus 0, which is the flux. So it makes it a little bit easier. Okay, so we go back up to the formula. Okay, we're looking for the EMF induced. Well, I'll just write that over here. That's what we're going to finish with. Okay, so we have, okay, so we have N, 200, we have the time, 0.2, we're missing the flux. So we have to find the flux. So up here, flux is B by A. So you would probably have done this first yourself. Okay, so B is 3 by 10 to the minus 3 by A. Now we don't have A, I should have got A originally. A is the area. So in this case, it's a circle, so it's pi r squared. So pi by 0.06 squared, but step by step. Okay, so pi by 0.06 squared. Okay, so we're getting 0.0113. And we'll be putting that in here. Yeah, so we're multiplying that by 3, and we're getting 0.0339, 0.034 Webers. Okay, so that's what we're missing from over here. That's why we started, remember. So we can just put that in here now. So we're multiplying that by 200. And dividing it by 0.2. And getting a value of 34 volts. Okay, so looking at that again, the so we had our formula. This time we didn't have the flux, so we had to go and get the flux. As it turned out, when we were getting the flux, we didn't have the area, so we get the area. So I'm kind of working that way. Most of you would have just said, okay, I'm going to get the area first, then I'm going to get the flux, then I'm going to get the EMF, because you know what's coming. Okay, I'm pretending I don't know what's coming. Okay, so question 4, sorry, the trickiest one. Okay, so square coil length 3 centimeters, so we'll just sketch that. Now let's get clear, we have the length of it, and then we also have the area of it. It's pretty obvious we're going to get the area, so let's put that in. So the area is 0.03 squared, so it is 9 by 10 to the minus 4. We have the length, which is 0.03. Okay, resistance is 2 ohms, so that gives you the warning. Ohm's law is on the way. 400 turns. Speed of 12 meters per second. Magnetic flux density is 75 by 10 to the minus 3. And you're asked for the EMF, the average EMF, and the average current as it enters the field. Now once again, it wasn't in the field, so the flux before was 0. Flux after is the maximum flux, so that will give us the change in flux. Okay, so I'll write it over here now, because I know I'm going to be doing all the work, so I'll put this over here. Right, I'm going to be finishing with this. Okay, right, so we don't have, okay, we're looking for the EMF. We have N, we don't have the time, we don't have the flux, so we'll have to go and get the flux. So the flux at the end, which will be the change of flux, B by A, so it's 75 by 10 to the minus 3, multiplied by the area, which is 9 by 10 to the minus 4, a very small value. So I have the 9 there, so multiplied by 75. Oh, something's gone wrong with the calculator. Somehow I changed the decimal. Okay, so 75 exponential minus 3 multiplied by 9 exponential minus 4. And we're getting, okay, I should have fixed this. Okay, I'm going to fix that there now. Set up FSE normal 2, remember. Okay, so 6.75 by 10 to the minus 5 vevers. We also don't have the time. Remember, if we don't have the time, we use velocity as distance over time. We were given the velocity, which was 12. The distance travelled from when it wasn't in the field to when it was in the field completely is the length of the coil, which is 3 centimeters. So that's 0.03 divided by the time. So the time will be 0.03 divided by 12. Okay, so we're getting 2.5 by 10 to the minus 3 seconds. So now we're in business. So the N is 400. The change of flux 6.75 by 10 to the minus 5. And the time 2.5 by 10 to the minus 3. Okay. So 400 multiplied by 6.75 exponential minus 5 divided by 2.5 exponential minus 3. Okay, so we're getting 10.8 volts. That's our answer. That's the average voltage. Okay, final one. Then we have the EMF. We're now asked for the current, so remember you put in your EMF here, 10.8. You're asked for the current, so pretty clearly it's Ohm's law. Okay, I is V over R, or I is E over R. So the voltage, the average voltage is 10.8. The resistance is 2, so it's 5.4 amps. There you go. Okay. Now, there are the basics. That's pretty much it. Okay, regarding Faraday's law. There are some questions which involve circuits as well, but we will come back to that when we combine everything at the very end. But basically, if you can do question 4 here, lads, you're in business, to put it mildly. Okay, thanks a minute.